everyone, from this lesson, we are getting to the part of acid-base titration. First, we start with the Lowry acid-base theory. From the chemistry class in middle school, we knew something basic about acid-base theory, and the deeper level of which came to be dug into in the diverse courses of chemistry in university. Chemistry teacher in middle school told us that in aqueous solution, substance from which ionized cations are all hydrogen ions is taken as acid, while a substance from which the ionized anions are all hydroxide is taken as base. The nature of the acid-base reaction is that hydrogen and hydroxide combine to generate water. This is the Arrhenius ionization theory put forward in 1894. However, as the emergence of more solvent and a wider range of application, this theory encountered a situation which was not able to explain, such as how to recognize the acid and base in non-aqueous solution. Sodium acetate was considered as salt in middle school, but its aqueous solution is basic. So, is sodium acetate a base? To solve such problem, in 1905, Franklin raised the solvent-based theory, which is that any solute producing characteristic cation of solvent is called acid, and those producing characteristic anion of solvent are called bases. This theory further develops the Arrhenius ionization theory and impacts on later research. The practical application is limited due to some disadvantages, such as restricted in auto-ionization solvent system and not available in system which cannot ionize. Then in 1923, 1Brønsted in Denmark and Lowry in England proposed independently the Brønsted-Lowry acid-base theory, which is that an acid is a substance capable of donating a proton, and a base is a substance that accepts a proton. This theory enriches the categories of acid and base, and expands the range of acid-base reactions, breaking the limitation that acid-base reaction must happen in aqueous solution. So, this theory is also applicable for acid-base reaction in non-aqueous and gas system, and classifies the dissociation, neutralization, and hydrolyzation reactions in water to the specific acid-base reaction of proton transfer. However, there is still defect in this theory. For example, it doesn't apply to compounds containing no hydrogen. This drawback was made up by another broader acid-base concept put forward in the same year by American chemist Lewis, which was influential in chemical field until 1930s. This theory holds that any molecule, group, or ion that can accept the electron pair is an acid. Any molecule, ion, or atomic group that can provide any electron pair is a base. The Lewis acid-base theory expands the range of acids and bases, and gets involved in many organic and solvent-free reactions. Its disadvantage is that this theory encompasses excessive categories, making the acid-base characteristics not obvious. Meanwhile, the strength order of the acid or base may be inconsistent if different reaction targets are selected. There is no unitary scale to determine the relative strength of the known acid and base, thus difficult to judge the direction of acid-base reaction. Later, this disadvantage was made up by the hard-soft acid-base theory proposed by Ralph Pearson. Of all these theories, the Lewis acid-base theory was the most extensively applied. Next, we are going to study this theory deeply. According to Lewis acid-base theory, the proton donor is called acid, while the proton acceptor is base. Based on this definition, we know that after an acid gives a proton, the corresponding ion can theoretically accept another proton. which means that the ion produced when an acid gives a proton is a base. Acid and base are produced simultaneously. One acid corresponds to one base, both of which are called the conjugated acid-base pair. Only one proton is transferred between the conjugated pair. Let's have a look at some examples. According to the above examples, we can conclude a reaction formula. A conjugated acid equals a conjugated base plus a proton. The second property of acid-base theory is that the acid-base reaction is the interaction of two pairs of conjugated acid and base. The aforementioned proton is expressed as hydrogen ion, which is a commonly hydrogen ion. The hydrogen ion is a bare nuclei with small diameter and positive charge. So just like electron, it cannot exist at the free state. The average life of hydrogen ion in water is only 10 to the minus 14 power second. So once hydrogen ion is produced, it will attach onto the solvent molecule and form an acid, which is hydronium in water. This reaction formula is listed here. According to the law of material conservation, there should be another pair of conjugated acid and base existing in the process of giving proton by acetic acid in aqueous solution, which is accepting the produced proton by a base. Here is a water molecule accepting the proton to form hydronium. However, it is not so convenient to write the proton and water molecule in the expression of acetic acid dissociation. So the reaction of proton with water to form hydronium is usually omitted, only leaving the dissociation of acetic acid as a final reaction formula. One thing to note is that only in writing we can do this omitting. The reaction of water should never be neglected, especially in the calculation of solution pH in later chapter. Similarly, let's have a look at the dissociation of base, taking ammonia as example. As a base, ammonia has a strong ability of accepting proton. Then, where these protons come from? We notice that water solvent itself keeps on dissociating proton and hydroxide ion to retain a dynamic equilibrium. Once ammonia is added into aqueous solution, it combines with free proton immediately to form ammonium ion, which dissociates proton simultaneously. It means that ammonium ion is actually the conjugated acid of ammonia. From the examples of acetic acid and ammonia, we can see that water molecule not only participates in the dissociation of acid, but in the same process of base, which means that water can both give and accept proton. This kind of material is called amphiprotic substance. Here is a simple conclusion. First, the transfer direction of proton is from the acid with strong ability of donating proton to the base with strong ability of accepting proton. The products of acid-base reaction are another kind of weak acid and base. Second, the reaction direction is from the strong acid to the weak acid. The third point of Lewis acid-base theory is autoprotolysis. We know that water is amphiprotic, so it can both give and accept proton. When the proton produced by water doesn't combine with another ions, it will react with water itself to form hydronium, which is one molecule of water decomposes to hydrogen and hydroxide ion. And the other molecule of water will react with this proton to form hydronium. The overall reaction is two molecules of water react to produce one hydroxide and one hydronium, which is usually called the autoprotolysis. The equilibrium constant of this reaction is called ion product constant with the expression of Kw, which is affected by the state of solution, such as temperature and pressure. At the standard state, Kw equals 10 to the minus 14th power when the activity value of pure water is taken as 1. Based on Lewis' acid-base theory, the strength of acid or base can be determined by their ability of giving or accepting proton. If the acid can easily donate a proton, it is considered as strong acid. The transfer of proton should happen between two conjugated acid and base. The strength of acid is meaningful only when compared with other acid. Generally, acid or base is compared with solvent to learn their strength. When the solvent is water, that is, in aqueous solution, it is to compare with water. The reaction equation of giving or accepting proton by acid or base in aqueous solution is listed here. The dissociation constant Ka and Kb can be expressed in this way with Ha as conjugated acid and A as conjugated base. The value of dissociation constant indicates the ratio of conjugated acid and base in solution, showing the strength of the acid or base. The larger the Ka is, the stronger the acid is. Similarly, the larger the Kb is, the stronger the base is. In order to distinguish their strength simply, dissociation constant of acid or base is commonly valued in negative logarithm. Based on the range shown in this table, there are 5 strength levels: strong, medium, weak, very weak, and extremely weak. The Lewis acid-base theory has told us that the conjugated acid and base appear in pair, so there is a certain relationship between the value of Ka and Kb, which is the product of Ka and Kb equals the ion product constant of water. For a monoprotic acid or base, the relationship between Ka and Kb is simple, the product of which is Kw. As for polyprotic acid or base, it is a little different, since the relationship refers to the conjugate acid and base. The dissociation constants of phosphoric acid have the relationship of Ka1 times Kb3 equals Kw equals Ka2 times Kb2 equals Ka3 times Kb1. That's all for today. Thank you.